The story of planet formation, Earth and beyond ****. Earth is an ancient planet, existing for more than 4.5 billion years, much like other planets that formed alongside the Sun. However, this time frame represents only a fraction of the universe's age, as planets likely predate Earth by billions of years. In the early universe, there were no planets, only vast clouds of hydrogen and helium gas. Over time, stars formed from this primordial gas, but the first planetary systems emerged only after these stars began enriching the cosmos with heavier elements, or metals. How planets form. The process of planet formation begins in cold gas clouds in space. These clouds, mostly composed of hydrogen and helium, collapse under gravity to form dense, hot seeds that grow into stars. Around these young stars, spinning disks of gas and dust, called accretion disks, form the building blocks of planets. As the temperature drops within the disk, dust particles condense, clumping together into larger chunks called planetesimals. These objects collide, merge, and grow over millions of years, forming planetary cores. Depending on their location in the disk. 1. Close to the star, rocky planets like Earth form. 2. Farther away, icy cores accumulate, potentially growing into gas giants like Jupiter or ice giants like Neptune, depending on the amount of material available. After about 10 million years, the disk clears, ending the planet formation phase. Understanding star metallicity and planetary age ****. A star's metallicity, its content of elements heavier than hydrogen and helium, reveals its age. Early stars lacked these metals, making planet formation impossible. As stars died and released metals into space, newer stars formed with higher metallicities, enabling planet formation. Stars with higher metallicity are younger, while older stars have less heavy elements. By studying a star's metallicity, scientists can estimate the age of any planets in its system. The search for exoplanets ****. Detecting exoplanets involves two main methods. Transit method, observing dips in a star's brightness as a planet passes in front of it. Radial velocity, wobble, method, measuring the gravitational pull of a planet on its star. Initially, these methods favored the discovery of massive, close-in planets called hot Jupiters. This bias led to the misconception that planets required high metallicity environments to form. Advances in technology, like the Kepler and Hubble telescopes, have since uncovered thousands of planets, including ancient ones. Methuselah, the oldest known planet ****. Discovered in the Messier 4 globular cluster, Methuselah is the oldest planet ever found, estimated to be 13 billion years old. It orbits a unique binary system, a neutron star, a dense, dead star, and a white dwarf, a smaller, dead star. Methuselah likely formed elsewhere in the cluster before gravitational interactions pulled it into this binary system. Despite the chaotic environment, the planet remains in a stable orbit, completing one revolution roughly every 100 years. Methuselah, the oldest known planet. If Methuselah, also known as PSRB 1620-26b, formed somewhere within the globular cluster M4, it is likely as old as the rest of the cluster. The approximately 100,000 stars in M4 were born together rapidly during the early universe. This makes Methuselah's age a staggering 12.7 billion years, nearly 3 times the age of Earth. This discovery challenges the long-held belief that planets require metal-rich stars to form. Primordial gas giant formation. The most fascinating aspect of Methuselah's existence is that it is a gas giant, more than 2.5 times the mass of Jupiter. Conventional expectations would suggest that ancient, low-metallicity star systems could only form small, rocky planets, given the limited metallic gas available at the time. However, Methuselah not only formed in this metal-poor environment but also amassed more mass than all the planets in our solar system combined. This raises questions about how it achieved such immense size. In the early universe, the core accretion process, where planetary embryos reach 10 Earth masses to attract a gaseous atmosphere, was unlikely to occur due to the lack of metals. Instead, Methuselah likely formed via a different mechanism that relied less on metallicity. In ancient, hydrogen, and helium-rich star systems, gravitational instabilities in dense primordial disks could have caused clumps of light gas to collapse into self-gravitating bodies. If these clumps became sufficiently massive, trace amounts of metal would have condensed into dust grains. These grains would have sunk to the center of the body, forming a makeshift planetary core and allowing the clump to function as a planet. Methuselah, formed in this manner, could sweep through its stellar disk, accumulating a massive hydrogen-helium atmosphere and becoming a super-Jupiter. Despite their rarity, such gas giants demonstrate that planetary formation was already underway within 1 billion years of the Big Bang. Kepler 444, the oldest rocky planets. If gas giants like Methuselah have existed for most of cosmic history, what about rocky, terrestrial planets? When did landscapes capable of overlooking the young cosmos first appear? Rocky core accretion builds planets from the ground up, meaning small terrestrial planets likely emerged before larger gas giants. These planets required some level of metals, taking longer to form than primordial giants like Methuselah. Among the oldest known rocky planets are those in the Kepler 444 system, located 119 light-years from Earth. This ancient triple-star system features a low-mass orange dwarf star orbited by 5 terrestrial planets ranging in size from Mercury to Venus. These planets, with an estimated age of over 11.2 billion years, show that terrestrial planets formed nearly as early as gas giants. Unfortunately, none of these planets are habitable, as they orbit too close to their parent star, rendering their surfaces scorched and lifeless. Nonetheless, their existence proves that both rocky and gas giant planets have been forming throughout the majority of the universe's history. The first habitable worlds. If terrestrial planets have existed for over 10 billion years, how soon after their formation could they support life? Habitable worlds require specific conditions: temperate atmospheres, chemical compounds, energy gradients, and liquid solvents like water. These conditions need to remain stable for hundreds of millions of years to allow the complex chain reactions of abiogenesis to occur. The first stars of the universe lacked sufficient chemical complexity and did not live long enough to support habitable planetary systems. Additionally, the early universe was flooded with supernovae and cosmic rays, hostile to potential biospheres. However, as star formation rates declined, galaxies likely began producing habitable rocky planets a few billion years after the Big Bang. The concept of the galactic habitable zone, regions with the right stability and metallicity for life, has evolved. Initially, scientists believed habitable zones were limited to areas rich in metals near galactic centers.